Welcome to Fundamentals of General Chemistry. In this video, we tackle gas theory. Let's get started. We begin with kinetic molecular theory. Just because particles are unapparent, emergent phenomena doesn't make them any less real. We presuppose a number of things in approaching gases. We presuppose that the collisions between these gas particles are perfectly elastic. And that's because if they weren't, then there would have to be some other sink for kinetic energy. But kinetic energy is conserved, and as we treat these gas particles ideally with minimal attractions and minimal repulsions, that means that the temperature of the gas will be proportional to the average kinetic energy of those gas particles. We also make an assumption that is perhaps not as intuitive, which is we are treating these gas particles as localized to such tiny space that we can treat their volumes, actual volumes, as non-existent. In reality, however, their volumes do have effects, especially when confined to really small spaces and high pressures. But before we derived anything from gas particles, we measured gaseous bodies, and we discovered four independent experimental relationships. That volume is proportional to the moles of gas. That volume is inversely proportional to the pressure. That volume is proportional to temperature, and that pressure is proportional to temperature. These were not theoretical. They were measured independently. Now, if we combine them and replace proportionality with equality by introducing a constant, we can rearrange and provide the ideal gas law equation. PV is equal to nRT, where R is the universal gas constant. This equation did not come from theory. It came from collapsing four empirical regularities into one single expression. But what is the meaning of R? R is the constant that allows energy, temperature, particle number, and volume to speak the same language. It is experimentally determined. It is universal. It does not depend upon the identity of the gas. And that universality is shocking. State changes can easily be derived from this relationship by solving for R. For two different states of the same gas, we can set P1V1 over N1T1 equal to P2V2 over N2T2. That means any gas transformation can be related directly. No new constants and no new assumptions. Just conservation of this universal relationship. Dalton's law is a subtle consequence of this. If pressure depends only on number of particles, temperature, volume, then identity does not matter. And so for mixtures, the total number of moles is equal to the sum of each index of moles. And that means then the total pressure is equal to the sum of each individual index of pressure. Dalton's law is not separate from ideal gas law. It literally falls out of it because pressure depends on particle number, not on particle identity. But PV is equal to nRT is the macroscopic version of this relationship. It relates pressure, volume, moles, and temperature through one universal constant, R. But R, experimentally, can be derived from simply taking 1 mole of gas at STP, standard temperature and pressure, The pressure being 1 atm, the temperature being 273.15 Kelvin or 0 degrees Celsius. And we experimentally determined that that mole of gas at STP occupies 22.414 liters of volume. If we substitute this in to our ideal gas law relationship, we get R is equal to 0.08206 liters atmosphere per Kelvin mole. It is important to note that liter atmosphere is the units of pressure times volume, which we have already encountered as a form of work. We can convert liters atmosphere to joules using the relationship 1 liter atmosphere is equal to 101.325 joules. And so in energy units, R becomes 8.314 joules per Kelvin mole. But if we look carefully, RT has units of energy per mole. RT is the thermal energy per mole of particles. This is profound. Temperature multiplied by a universal constant gives us energy. Temperature is not quote-unquote hotness. It is an energy scale. But a mole is not fundamental. A mole is just a counting unit. Mole is equal to the total number of particles divided by Avogadro's number, where Avogadro's number is 6.022 times 10 to the 23rd. And we can substitute that into the ideal gas law and rearrange and define Boltzmann's constant, Kb, as R divided by Avogadro's number. And that gives us PV is equal to the total number of particles times kBt. Notice the units of kBt. It is energy per particle per Kelvin. This is thermal energy per particle. With the thermal energy per particle in mind, we go down a route of deriving an exact relationship between temperature and the movements of the particles. We start if we consider just one particle traveling along the x-axis in the volume of a cube. Recall that momentum is equal to mass times velocity. The initial momentum of this particle is equal to mass times the velocity of it traveling in the x-axis. Its final momentum is equal to negative mass times velocity in that x-axis. If we want to find the change in momentum of that particle, it would be equal to the final momentum minus the initial momentum, or negative mvx minus mvx, which is equal to negative 2 mvx. The change in momentum of the wall would just be negative change in momentum of our particle, and that's positive 2 mvx. Recall that vx, the velocity, is the displacement, the change in position of x over the change in time. And the change in position is just simply 2 times the length it traveled. If we rearrange that relationship to solve for change in time is equal to 2 times the length over the velocity in the x-axis. With that in mind, we can now talk about the force being applied against the wall, because pressure is force divided by area. Force is equal to mass times acceleration. We can substitute in for acceleration change in velocity over change in time. And that gives us mass times change in velocity over change in time. With mass times change in velocity, we clearly see that that's equal to change in momentum, specifically change in momentum of the wall over change in time. We can substitute in for the change in momentum of the wall, and we can substitute in for the change in time. And we get mvx squared over L. Now, we want the total force being applied against all the particles traveling in the x-axis. And that's going to be equal to the sum from from index 1 to up to n particles. And that's going to be the sum of each mvx squared over L. We notice that m mass of those particles, assuming that we have the same particles, is going to be the same. And so that's constant, and the length is constant. So mass over length times the entire sum of the velocities of those individual particles squared. Notice the definition of average. Average is just equal to the sum of each individual number in that set divided by the total number, right? And so we can apply that definition of average in terms of average velocity. The average velocity of x particles squared is equal to 1 over the total number of particles times the entire sum of each of those velocities of particles traveling in the x-axis squared. If we solve for the sum, which is literally what we have in that force relationship above, we can solve for that in terms of the n total number of particles times the average of the velocities of all the particles in the x-axis squared. And we can substitute that in, and we realize that at equilibrium, the velocity distribution must be what we call isotropic. That means that nature won't favor any particular dimension over another. And therefore, the average velocities of the particles in the x-axis will be equal to the average velocities also in the y-axis and in the z-axis. In reality, we use vectors to represent the individual velocities of particles comprised of x, y, and z components. For a vector velocity squared, we would multiply vectors, and this would result in a dot product, as you can see the matrix notation provided. This would be equal to vx squared plus vy squared plus vz squared. And because averaging is linear, the average of v squared equal to the average of vx squared plus vy squared plus vz squared would be also equal to the average of vx squared plus the average of vy squared plus the average of vz squared. And given that no dimension is favored, then the average of vx squared is equal to the average of vy squared, which is equal to the average of vz squared. Therefore, the average velocity is equal to 3 times the average velocity of vz squared. And we can substitute that relationship into our last equation. And given that pressure is equal to force divided by area, and that we chose a cube, and so the area of a cube is L squared, we can simplify to the volume of a cube, and multiplying both sides by v, we get the relationship 3 PV is equal to the total number of particles times the mass times the average of their velocities squared. We recall that the kinetic energy of any body or particle is equal to 1/2 mv squared. So the average kinetic energy would be equal to 1/2 m times the average velocity squared. And we can see our relationship is almost closely related to that. So we can divide both sides by 2, and then we can substitute in for 1/2 m times the average velocity squared. And so we get 3 halves PV is equal to the total number of particles times the average kinetic energy. And recall that our internal energy of our particles is equal to the total number of particles times the average kinetic energy. So now we have a fundamental relationship derived between internal energy and the temperature of all monoatomic gas particles. Internal energy is equal to 3 halves nRT. And what is so fundamental about internal energy equal to 3/2 nRT? There is clearly a fundamental relationship between the temperature of the gas particles collectively and how the energy is being distributed among them. This refers to the equipartition theorem, because kinetic energy depends upon the velocity squared in each direction, and because nature treats x, y, and z axes identically, temperature distributes energy equally among those degrees of freedom. And you can see the similarity in the equation with internal energy equal to 3/2 NkBT as equal to n, the total particles, times 1/2 kBT plus 1/2 kBT plus 1/2 kBT. And that, by inspection, is corollary to the relationship of n times 1/2 m average velocity in the x-axis squared plus 1/2 m times average velocity in the y-axis squared plus 1/2 m times average velocity in the z-axis squared. This means that if kinetic energy has been added to the particles of any given system, the average kinetic energy of the particles, proportional to temperature, will increase. But how much the temperature will change will be dependent upon how that substance distributes the kinetic energy. We can generalize this for internal energy, that it's equal to F over 2 times nRT, with F being the degrees of freedom. The greater the degrees of freedom a substance has, the less that temperature of that substance will change. And this directly connects to heat capacity. The ability of a substance to quote unquote hold heat really refers to the ability of that substance to distribute kinetic energy among its individual degrees of freedom. It is literally, heat capacity is literally the slope of internal energy with respect to temperature, with, of course, volume being constant. Furthermore, what's pretty insane is that we can use these simple principles that we've derived to find the velocity, the average velocity of the individual particles of any gas. Because translational motion is only in 3 dimensions. So internal energy equal to 3/2 nRT, we can set that equal to the total number of particles times 1/2 m times the of the average velocity squared. And multiplying both sides by 2, we can simplify. Substitute in for moles equal to the total number of particles divided by Avogadro's number. We can simplify and notice that the molar mass is equal to the mass of each of the individual particle times Avogadro's number. And we can simplify and we get the square root of the average velocity squared. This is what's called the root mean squared velocity. We simply can't just simplify it to the velocity of a particle because that would be effectively meaningless given the fact that all of these particles are traveling in all different directions. The more massive particles, though, based upon this relationship, will travel slower at a given temperature. What is amazing is that this equation only relates temperature and molar mass as variables. Everything else is constant. And so this applies to all ideal gases. This internal energy relationship has allowed for the determination of velocities and as well as relative velocities if we wanted to compare particles to each other. You see that on the below our root mean square velocity, we can relate two velocities of two different particles to each other. And all we have to do is simplify and we get Graham's law of effusion, which relates the velocity of one particle to the velocity of another, again, root mean squared, but that's simply equal to the square root of the molar mass of the second particle divided by the molar mass of the first particle. We end this video considering deviations from ideal gas behavior and attempts to explain them. Under extreme conditions, when gas particles are brought closer together at high pressures and low temperatures, more attractions are possible as collision frequency increases, and there are more frequent attractive interactions between partner particles. But if we make the volume even closer, even smaller, we actually get another phenomena where repulsions increase enormously as the constraints of volume force electrostatic fields to overlap. Uh, and in order to derive how we might approach this, we would consider the fact that for any real pressure of real gas particles, it would be equal to the ideal pressure minus some kind of factor based upon attraction, because the attractions will decrease the pressure. But this will be related to the concentration of the particles, moles divided by volume. If you notice here, we introduced the idea of probability because we are talking about partners, particle partners that would attract each other. And so we can't just consider one particle by itself. We have to consider partners. And so the probability of partners, pairs colliding, would be the probability of one times the probability of the other. And so we get the concentration squared. Of course, we introduce A as just some factor that's specific to the identity of that substance. So the real pressure of any gas system would be equal to the ideal pressure minus A times the concentration squared. And so we can solve for that in terms of the ideal pressure. For the actual volume of the container, it would be equal to the volume of the container minus the volume of the individual gas particles, which again would be different for each different substance, and we can represent that by a factor, a constant B times the moles of those gas particles. And if we substitute into PV equals nRT, we derive the van der Waals real gas law equation. Well, that summarizes all of the deep relationships of gas theory that's referred to in general chemistry, as well as making connections a bit deeper and establishing concepts that we will refer to in future videos. Till next time, Crip.